These are your mole notes. You should be taking notes over these in your journal. So in chemistry, it's a quantitative science, which just means that quantitative means it has numbers. And so that means that we need a counting unit. And in this case, we use what's called the mole. 1 mole is the amount of substance that contains as many particles. So whenever I say the word particles, I could be meaning either atoms or molecules, as there are in 12 grams of carbon-12. All right. So because if you think about whenever you're doing math, or really even just trying to visualize atoms, it's really hard to think about what's happening at the atomic level, right? And so whenever we're using the mole, it just makes something that's so small a little bit easier for our minds to think about and to do things with. So the person who kind of led to this was Amadeo Avogadro. And he said that 1 mole was equal to a lot of particles, or 6.022 times 10 to the 23rd. So if you'll kind of look how it's broken up, it's way, way, way bigger than trillions or quadrillions, right? And so 6.022 times 10 to the 23rd in scientific notation is how we talk about Avogadro's number. So there's that many particles, again, either atoms or molecules, in a mole of any substance. Oh my goodness. So how big is a mole? So here are just some examples. 1 mole of marbles would cover the entire Earth, oceans included, for a depth of 3 miles. That's a lot of marbles. 1 mole of a $100 bill stacked one on top of another would reach from the sun to Pluto and back 7.5 million times. And it would take 9,500 light years to travel from the bottom to the top of a stack of 1 mole of $1 bills. That's a lot. That's a big, big number, right? So Avogadro's number, again, is a mole of any substance that contains as many particles as the number of atoms in 12 grams of the isotope of carbon-12. So that's called Avogadro's number, which can be represented in with a little a. The mass of 1 mole of substance is called molar mass, symbolized by a capital MM, and those units are grams per mole. So if we think back to what we just did using molar mass, right, I kind of just told y'all that it's grams per mole. And what that's saying is that there are this many grams of these kinds of particles. So in the case of H2, it'd be molecules, right, because there's 2 of them, in 1 mole of substance. Or if I'm talking about carbon dioxide, there are 44 grams in 1 mole of carbon dioxide. Okay. So here's a brief look at how we're going to do stoichiometry. Again, stoichiometry, if you go back to your molar mass notes, is just the mathematical study of what's going on with atoms. And so this is really where we introduce Avogadro's number. So we're going to copy this down in a moment. I just want to talk through it, so you do not need to write anything. All right, you're just listening. So whenever I'm trying to think about going from mass of one substance, so this side is substance A, and this side is substance B. If I'm trying to figure out how I can go from the mass of substance A to the amount of particles of substance B, or anywhere in between, right? Mass to moles of the other substance, whatever the case may be, I have these conversion factors here over the arrows, right? In order to go from mass to mole or mole to mass, I use the 1 mole equals the molar mass, or grams per moles. If I'm going from volume to mole, you're using the standard temperature and pressure. 1 mole is equal to 22.4 liters of a gas. If I'm going to particles, this is where I use Avogadro's number. So 1 mole is equal to 6.022 times 10 to the 23rd particles. In order to go between two different substances, so this is the first time that we're doing that in this class, we have to use coefficients from a balanced chemical equation. So this is where it becomes very important to start off with a balanced chemical equation. All right, so don't copy this down. We'll do this at a later time. So if we're trying to think about a chemical reaction, we have sodium over here, we have chlorine atoms, and we're trying to make sodium chloride or salt. So I have 10 moles, right? If I have 10 little atoms of sodium, 5 particles of chlorine 2, right? If I'm counting them up, I want to know how many moles of sodium chloride I will make. All right, so it ends up being 10. And so here's my balanced equation. But like fractions, balanced equations can be reduced if they have a common denominator. So in this case, they all had the same common denominator of 5. And so when you divided all of them by 5, you got 2, 1, and 2. So this is my balanced chemical reaction. Okay. So stoichiometry is a mass relationship between substances in a chemical reaction, and it's based on the mole ratio. So the mole ratio refers to the ratio between different parts of a balanced chemical equation. Okay. So if I'm looking at the mole ratio between magnesium and oxygen, it would be 2 to 1. Right? If I'm looking at the ratio between magnesium and magnesium oxide, it'd be 2 to 2, or since it's a ratio, you could reduce it to 1 to 1. All right? So that's the mole ratio is the coefficients. So here are the steps to stoichiometry and performing a calculation using stoichiometry. Number 1, write a balanced equation. So you always start off with a balanced equation. If you're not sure what to do, just start there. Number 2 is to identify the known and the unknown. All right, so what is it giving you and what are you trying to get to? Number 3, list necessary conversion factors. All right, so that's thinking about am I using my molar mass or Avogadro's number, or maybe something that has to do with a liquid or a gas. And number 4, set up the conversion table using your graphic organizer. And we're going to make our graphic organizers in a little bit. Multiply across the top, multiply across the bottom, then divide. So if you'll think back to these last 3 steps, whenever last semester we did dimensional analysis, which was just converting different units to different things, right? So we went from feet per hour to centimeters per second, things like that. It had the same kinds of steps. So this will actually look a lot like dimensional analysis. The table will look the same. The last steps will look the same. It's what we're putting in it that will be a little bit different. And again, I will work some of these examples so you can see how that's done. And don't forget to include the correct units for your answer, right? The whole purpose of this is to convert between different things. And so if you're not sure, if your teacher's not sure what you're doing, it's hard to give partial credit. So always, always, always include units for your answer. So how many moles of potassium chlorate must decompose in order to produce 9 moles of oxygen gas? So again, I start with my balanced chemical equation. And this would be something that's given to you, probably not balanced. That will be something that you are doing, but the base chemical equation will be given to you. So I have my balanced chemical equation. I know my known and my unknown, right? I know that I have 9 moles of oxygen gas. and I want to know how many moles of potassium chlorate I have. So I start there, and I know that the conversion factor in this case, I'm only going from moles to moles, will be this mole ratio, so 2 and 3. So I put my given, which is 9 moles of oxygen, right here. And then remember, if I'm trying to cancel out moles of oxygen, that goes on the bottom. So moles of oxygen goes on the bottom here. And the 3 comes from my mole ratio right here. And I know that it's 3 to 2, right? So it's equal to 2 moles of potassium chlorate. So I've canceled out moles of oxygen. I'm in moles of potassium chlorate. That's what I'm trying to get to as my unknown. So I would multiply across the top, right, which is 18. Multiply across the bottom, and it ends up only being 3. And so 18 divided by 3 is 6 moles of potassium chlorate. So these are the kinds of problems that you would get. So this is just visualizing using the graphic organizer, right? We're just going from moles of O2 to moles of potassium chlorate, and we use our mole ratio to do so. Okay. So how many grams of potassium chlorate are required to produce 9 liters of O2 at STP? So again, I have my balanced chemical equation. I want to know, my unknown is grams of potassium chlorate, and my given is 9 liters of oxygen gas. So I'm going to put my given 9 liters of oxygen right here. And remember, if I want to cancel out liters of oxygen, it goes on the bottom. So liters of oxygen, liters of oxygen. And I know that the 22.4 liters of oxygen is equal to 1 mole. Again, this is my conversion factor. So those cancel out. Then if I'm trying to get out of moles of oxygen, I want to put the new moles of oxygen on the bottom. So 3 moles of oxygen is equivalent to 2 moles of potassium chlorate from my coefficients here. So I've canceled out moles of oxygen. And the last problem, we stopped here at moles of potassium chlorate, but remember, we're trying to get to grams. And so the way that we go from moles to grams is using the molar mass. So if I were to calculate the molar mass of potassium chlorate, I would get 122.55 grams per 1 mole. All right, so this is a different kind of way of writing the molar mass, where I have the grams up top, and then the per 1 mole goes on the bottom. And that allows me to cancel out my moles of potassium chlorate. I multiply across the top, get a number, multiply across the bottom, get a number, and then divide. And then I get 32.8 grams of potassium chlorate. So this is really helpful. So if you're working in a lab and you're like, okay, I need to make 9 liters of oxygen, how much of this do I need to start off with? Right? So it's good at predicting what you need for a chemical reaction to take place. All right, that is all. Make sure you have all of your notes written down and that you come and show them to Miss Harvey.